Let's now focus on the property of these magnetic forces. The direction of the magnetic force is unique. It is always perpendicular to both the velocity of the charge v and the magnetic field B. This means the force is not in the direction of motion nor in the direction of the field, but perpendicular to the plane contains both of those vectors. To determine this direction, we use the right-hand rule. For a positive charge, you point the fingers of your right hand in the direction of the velocity v, then you curve your fingers in the direction of the magnetic field B. Your thumb will now point in the direction of the magnetic force F. If the charge is negative, the force in the exact opposite direction of your thumb. So this is called the right-hand rule. Since the current is just a moving charge, a current carrying wire also creates a magnetic field. We have a second right-hand rule to find its direction. You grasp the wire with your right hand so that your thumb points in the direction of the current. Your fingers will then curl around the wire in the direction of the magnetic field length. This shows the field forms concentric circles around the wire. So this picture shows us what the magnetic field length actually looks like for a non-straight wire. We can also calculate the magnitude of this field generated by a non-straight wire. It's given by B equals to mu0 I 2 pi r. And mu0 is a constant. Its magnitude is given by 4 pi times 10 to the negative 7 Tesla times meter per ampere. Mu0 is called permeability of the free space. And in this equation, mu0, of course, we just discussed, I, current of the non-straight wire, and r is the distance from the wire. Suppose this is I, then this is how we calculate the magnetic field for a circle around the wire with distance r to the wire. We can also generate a magnetic field using a ring current. Now all segments of the wire contribute to the field at the center. For coil with n loops, the field at the center is given by the equation n times mu0 I 2r. I is the current the ring carries. R is the radius of the ring. N is how many loops of wire we have. If you look at the pattern of magnetic field length for current loop, you will see that it is remarkably similar to the field of bar magnets. A current loop creates a magnetic dipole field. To create a stronger field, maybe more importantly, to create a uniform magnetic field, we can wound a wire into a long coil called a solenoid. A solenoid acts as an electromagnet because it only behaves like a magnet when there is a current flowing through it. The field of a solenoid is very interesting. Inside the solenoid, the field lengths are parallel, uniformly spaced, and close together. This indicates the field is very strong and uniform. Outside of the solenoid, the field is much weaker and non-uniform. As you can see by comparing those two images, the magnetic field outside a solenoid is nearly identical to the field of a bar magnet. The end where the field lengths emerge acts as a north pole, and the end where they enter acts as a south pole. The great advantage of a solenoid is a strong, constant magnetic field inside it. The magnitude of this field is given by the simple equation mu0 n I, where n is the number of turns per unit length. This shows the field strength depends on the current and how tightly the wire is wound. This concludes our discussion of electricity and magnetism.